Preparing for a Java developer at MUFG interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How does Java achieve platform independence, and what happens when you run a Java program? Java source code is compiled into platform-neutral bytecode by JAVIC. The JVM then loads, verifies, and executes that bytecode on the target operating system. Hot methods are optimized by the just-in-time compiler into native machine code, improving performance during long-running workloads. This separation supports portability, while the JVM supplies garbage collection, security checks, and runtime services. In banking systems, I would also verify the deployed JDK version in JVM settings across environments. While answering, explain source compilation, bytecode, the JVM, class loading, JIT compilation, operating system independence, and why JVM implementations can still have performance or compatibility differences. Question 2. What is the difference between equals and equals in Java, and how would you use them safely? For primitives, equals compares values. For objects, it compares references. The equals method should compare logical content, such as two customer objects with the same identifier. String literals can make equals appear correct because of interning, but that is unreliable. I use constant first comparisons or objects, equals for null safety. Whenever I override equals, I override hash code consistently, otherwise hash-based collections may lose or duplicate logically equivalent entries. Make sure to cover primitive value comparison, reference identity, logical equality, string behavior, null safety, equals hash code consistency, and implications for collections such as HashMap and HashSet. Question 3. Explain Java's memory model and the difference between stack, heap, and metaspace. Each thread owns a stack containing method frames, local variables, and references. Deep recursion can cause stack overflow error. The heap stores objects shared across threads and is managed by garbage collection. Metaspace stores class metadata and grows outside the traditional heap. A memory leak in Java usually means reachable objects are retained unintentionally, such as unbounded caches or listeners. I would diagnose issues using heap dumps, allocation profiles, and GC logs rather than guessing. In your answer, distinguish thread local stack frames from shared heap objects, describe metaspace and class metadata, mention object lifetimes, garbage collection, and common causes of stack overflow or out-of-memory errors. Question 4. How does garbage collection work, and how would you investigate a production latency problem caused by GC? Garbage collection identifies unreachable objects and reclaims their memory. Most collectors exploit generational behavior. Short-lived objects are collected frequently, while survivors move toward older regions. For latency spikes, I would inspect GC logs, pause duration, allocation rate, heap occupancy, and Java flight recorder events. I would then check object churn, oversized caches, and heap settings. The right collector and configuration depend on workload, so I would validate changes with production-like load tests. Be sure to mention reachability, generational collection, young and old generations, pause times, allocation rates, heap sizing, GC logs, JFR, and balancing throughput against latency requirements. Question 5. What are the key object-oriented design principles you apply when building Java services? I use encapsulation to protect invariants, interfaces to define stable contracts, and composition to assemble behavior without rigid inheritance hierarchies. Solid principles help, especially single responsibility and dependency inversion, because services become easier to test and change. For example, a payment service can depend on a payment gateway interface rather than a specific provider. I avoid abstractions that merely add indirection. In regulated systems, clarity and traceability are also design requirements. Focus on encapsulation, abstraction, polymorphism, composition over inheritance, solid principles, dependency inversion, testability, and avoiding over-engineering or excessive abstraction in financial applications. Question 6. How would you design an immutable Java class for a financial transaction? I would make the class final, keep fields private and final, validate inputs in the constructor, and expose no setters. Any mutable input, such as a date or collection, must be defensively copied. Returned collections should be unmodifiable. Monetary values should use big decimal with an explicit scale and rounding policy, not double. Immutability makes transaction objects thread safe, easier to cache, and safer to audit because their state cannot change after creation. Mention final class or controlled inheritance, private final fields, constructor validation, defensive copies, no mutators, immutable nested objects, big decimal for money, and safe publication across threads. Question 7. When would you use an interface, an abstract class, or composition in Java? I choose an interface when different implementations should satisfy the same contract, such as multiple fraud checking strategies. An abstract class is useful when related implementations genuinely share protected state or substantial workflow. Composition is my default for combining behavior because it reduces coupling and supports runtime substitution. Interfaces also allow multiple capabilities through implementation, while abstract classes impose single inheritance. The decision should follow domain relationships, testing needs, and expected change, not personal preference. Explain interfaces as contracts, abstract classes as shared state or behavior, composition as flexible collaboration, default methods, multiple interface implementation, and maintainability considerations for evolving APIs. Question 8. How do HashMap and ConcurrentHashMap differ, and what mistakes commonly occur when using them? HashMap is not thread-safe and permits one null key, while ConcurrentHashMap supports concurrent access and rejects null keys and values. Both depend on stable hashcode and equals implementations. ConcurrentHashMap improves scalability through fine-grained coordination, but a sequence such as contains key followed by put is not atomic. I use compute if absent, put if absent, or merge for compound actions. Keys must be effectively immutable. Changing key fields after insertion can make entries unreachable. Cover hashing, buckets, collisions, equals hashcode, null handling, thread safety, atomic methods, resizing, iteration behavior, and why synchronized access may still be required for compound operations. Question 9. What is the Java Stream API, and when should you avoid using streams? Streams provide a declarative way to transform and aggregate data through lazy intermediate operations followed by a terminal operation. For example, I can filter active accounts, map balances, and collect results without manual loop bookkeeping. I avoid streams when logic has complex branching, requires checked exception handling, or becomes harder to debug. I also avoid parallel streams in shared server pools unless measured carefully, because contention, ordering, and blocking operations can hurt reliability. Discuss declarative processing, intermediate versus terminal operations, laziness, collectors, side effects, parallel streams, readability, debugging, and database-related performance considerations. Question 10. How do checked and unchecked exceptions influence API and service design? Checked exceptions force callers to acknowledge recoverable conditions, such as a file or external resource failure. Unchecked exceptions suit programming errors or failures a layer cannot reasonably recover from. I define meaningful domain exceptions, preserve the original cause, and translate low-level exceptions at service boundaries. I avoid catching exception broadly unless I can add context or recover. In a REST service, centralized handling should return stable error contracts while logging correlation identifiers securely. Explain compile time handling, recoverable versus programming failures, domain-specific exceptions, cause preservation, centralized handling, transaction boundaries, logging, and avoiding swallowed or overly generic exceptions. Question 11. How would you make a Java service thread safe when processing concurrent account transactions? I would minimize shared mutable state and keep request processing stateless. Account updates need a database transaction with appropriate isolation or optimistic version checks, rather than relying only on Java synchronization, especially across multiple service instances. For in-memory counters, atomic long or carefully scoped locks may be sufficient. I would enforce idempotency keys, validate account versions, and record an audit event. Correctness comes from coordinating application, database, and messaging boundaries together. Cover shared mutable state, synchronization choices, atomic operations, locking scope, transaction isolation, optimistic versus pessimistic concurrency, idempotency, and avoiding double spend scenarios. Question 12. What are the differences between synchronized, ReentrantLock, volatile, and atomic classes? Synchronized provides mutual exclusion and visibility with automatic lock release. ReentrantLock offers features such as timed acquisition, interruptible waits, and fairness, but requires careful unlocking and finally. Volatile guarantees visibility and ordering for individual reads and writes, not compound operations like increment. Atomic classes use compare and set for lock-free updates when suitable. I start with synchronized or immutable design, then choose more specialized tools only when measured contention or coordination requirements justify them. Make sure to explain mutual exclusion, visibility, ordering, reentrancy, interruptible and timed locking, compare and set, compound operations, and choosing the simplest correct concurrency primitive. Question 13. How would you use CompletableFuture in a Java service that calls multiple downstream systems? I would start independent calls asynchronously on a deliberately sized executor, combine successful results with then combine or all of, and apply explicit timeouts. Each future should translate failures predictably, with fallback only when business safe. I avoid blocking the common pool and ensure request context, tracing, and security data are propagated appropriately. For a banking workflow, partial responses must not imply a completed transaction. Asynchronous code improves latency, but it increases observability and failure management complexity. Discuss asynchronous composition, parallel independent calls, then combine and all of, executor sizing, timeouts, exception handling, cancellation, context propagation, and avoiding blocking common pools. Question 14. How do you prevent SQL injection and manage database access in a Java application? I use parameterized queries or properly bound ORM parameters, never string concatenation with user input. Validation still matters for business rules, but it is not a substitute for query parameterization. Database accounts should have least privilege, credentials should come from secure configuration, and connection pools need sensible limits and timeouts. I define transaction boundaries at the service layer, monitor slow queries, and audit sensitive operations without logging account numbers or personal data unnecessarily. Mention prepared statements or parameter binding, ORM query safety, input validation, least privilege credentials, transaction boundaries, connection pooling, secret management, and auditing sensitive access. Question 15. What transaction isolation level would you choose for a money transfer, and why? A transfer should update both accounts atomically, so I would use a database transaction with a carefully selected isolation level, usually at least read committed plus explicit consistency checks. Serializable may be appropriate for highly conflicting operations but can reduce throughput. I would use stable lock ordering or optimistic versioning to prevent lost updates and reduce deadlocks. The choice depends on database behavior and volume. I would validate correctness with concurrency tests, not assumptions. Cover atomicity, consistency, isolation, durability, dirty and non-repeatable reads, phantom reads, locking, optimistic concurrency, deadlocks, and matching isolation to business correctness and throughput. Question 16. How would you design a reliable REST API for a banking operation such as initiating a payment? I would model payment initiation as a resource and return a clear status, such as accepted or completed, rather than pretending asynchronous work is synchronous. The endpoint would require authentication, authorization, validation, an ID impotency key, and a correlation identifier. Responses would use stable error codes and avoid sensitive details. I would version breaking changes, apply rate limits, audit state transitions, and document retry behavior so clients cannot accidentally submit duplicate payments. Focus on resource modeling, HTTP semantics, validation, authentication and authorization, ID impotency, consistent error responses, versioning, auditability, rate limits, and sensitive data protection. Question 17. How would you integrate a Java application with a legacy banking system or external payment provider? I would isolate the legacy protocol behind an adapter with a modern domain interface, keeping provider-specific formats out of core business logic. Calls need TLS, authentication, strict timeouts, bounded retries, and circuit breaking. Retries must be idempotent because a timeout can occur after the provider accepted the payment. I would persist request identifiers, reconcile uncertain outcomes, expose metrics and traces, and test contract compatibility using simulators and representative failure scenarios. Mention adapter boundaries, contract mapping, timeouts, retries, circuit breakers, ID impotency, reconciliation, schema evolution, observability, secure transport, and handling ambiguous outcomes safely. Question 18. What testing strategy would you use for a Java service handling financial transactions? I begin with fast unit tests for validation, calculations, and state transitions, using realistic edge cases such as rounding and duplicate requests. Integration tests verify database transactions, messaging, and provider adapters. Contract tests protect service boundaries. I add concurrency, security, and performance tests for critical paths, especially retry and timeout behavior. Test data must be isolated and synthetic. C should gate changes, while production telemetry and controlled failure tests reveal gaps after deployment. Include unit, integration, contract, end-to-end, property-based, concurrency, security, and performance testing, plus test data isolation, deterministic behavior, mutation testing, and production-like failure scenarios. Question 19. How would you troubleshoot a slow or failing Java microservice in production? I first define the symptom using request rate, error rate, latency percentiles, and affected endpoints. Then I correlate dashboards, structured logs, traces, thread dumps, GC data, database metrics, and downstream health. I check recent deployments or configuration changes and compare healthy versus failing instances. During an incident, I stabilize first through rollback, scaling, or traffic control, then investigate deeply. I document the root cause and add a regression test or alert afterward. Be sure to cover symptom definition, metrics, logs, distributed traces, thread dumps, heap and GC analysis, database latency, dependency health, recent changes, rollback, and safe incident communication. Question 20. How do you approach security, compliance, and sensitive data handling in Java applications at a financial institution? I treat security as part of design, not a final checklist. I enforce strong authentication and authorization, validate inputs, use TLS, encrypt sensitive data appropriately, and store secrets in a managed vault. Logs should contain correlation information but mask credentials, tokens, and personal account data. Dependencies require scanning and timely patching. I also design auditable state changes, apply least privilege, review threat models, and ensure controls match applicable regulations and internal MUFG policies. Discuss secure coding, authentication, authorization, encryption in transit and at rest, secrets management, dependency scanning, input validation, audit trails, privacy, masking, and least privilege access. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.